Understanding how an engine and propeller works is something all pilots must know and will be tested on both in terms of written exams and by flight testing. Some people have a hard time understanding the key concepts because it's hard to visualize. Fortunately, we've packed lots of animations into this section to help you see how the power plant works. We'll talk about reciprocating engines, opposed engines, four-stroke engines, carburetor systems, magnetos, and ignition, and how a power plant changes the up and down motion of a piston to the rotating motion of a propeller. Here's a typical aircraft engine. This is the side view. The front of the engine is on the right, and the propeller would attach to the piece shown on the image. You can also see that there are 4 cylinders. Each of those silver covers has a cylinder behind it. There are 2 on this side of the engine and 2 on the other side. Because of this, the engine is called an opposed engine. Basically, the cylinders work with one another on opposite sides of the engine. More on that a little later when we see the motion of the pistons in the cylinders. Also toward the back of the engine, you'll see an arrow pointing toward the magnetos. There are 2 on this engine. One is shown here, and the other is on the other side of the engine. The magnetos produce the spark for ignition. Again, more on magnetos a little later. Here's a top view of the engine we saw on the previous slide. The term reciprocating means a back and forth motion. If you look at each of the cylinders, you can imagine them as a housing or case that contain a moving piece that goes up and down. This is called a piston. The red bar in the middle is a shaft that is connected to the pistons that will take the piston's up and down motion and convert it into a rotation. You can also see that the cylinders are on opposite sides of the engine. In this animation, you can see the cylinder walls to the left of the image. Inside, you can see a big plunger-type device moving. This is called a piston. On the other side, you can see the opposed piston moving in time with the one on this side. We didn't show the case of the cylinders on the right side of this animation to help you see the motion a little better. So here you can see how the back and forth motion of a piston can be used to turn a crankshaft which turns the propeller. So now that we have seen the whole thing turning, we must ask ourselves, what makes the piston go back and forth in the cylinder? The answer is in understanding the 4 strokes of an engine. The concepts of the engine we use today was developed by a German scientist called Otto. He made the first of this kind of engine, and we call it the Otto cycle or Otto engine. First, I'll describe how it works by using the image above, and then we'll see a couple of animations to help you visualize it and understand it better. First, if you look at the image, you'll see at the top left that there are 2 valves at the top of the cylinder. These valves are the intake valve and the exhaust valve. Let's see how the 4 strokes work by going through each of the cycles. First, in the top left, the intake valve pushes into the cylinder. This allows air and fuel to be moved into the cylinder. The piston is moved down and this creates suction. The exhaust valve is closed, so the piston is producing quite a bit of suction and pulling the fuel and air into the cylinder. Now moving to the top right, both valves close and the piston begins moving up. This action causes the fuel and air in the cylinder to compress into a smaller space. Now moving to the bottom left, as the cylinder reaches the top and starts down again, the spark plugs on the sides of the cylinder ignite the fuel and air that is in the cylinder. This causes the piston to be pushed down into what is called the power stroke. Over on the bottom right, we now see that the piston is coming back up and the exhaust valve opens. This allows the burned gases to escape to the outside. This whole process is repeated until we either stop the ignition or turn off the fuel or air to the engine. So here is the animation of the engine. Notice how the valves work with the piston to create the 4 strokes. You might be asking where this fuel and air comes from to get pulled into the cylinders. This animation lets you see the whole picture. You can see the engine busy with its 4-stroke cycle. You can also see on the left side near the bottom is a little box. This is called a carburetor and takes fuel from the tanks and sends just the right amount into the pipe. This pipe is called the intake manifold. Air comes from the outside through a part of the carburetor and mixes with the fuel to form the correct mixture of fuel and air. We'll see how the carburetor works in just a few minutes. Notice that when the exhaust valve opens, the burned gases now vent outside through the exhaust manifold. Remember that this is just one cylinder shown here. Most aircraft use either 4 or 6 cylinders. So what is the purpose of the carburetor? It supplies fuel to the intake manifold. It is controlled by the pilot by the throttle setting and the mixture setting inside of the cockpit. A 3D image of a carburetor is shown here. Notice the fuel supply on the right and the little jet coming into the venturi. If you remember from the aerodynamics presentation, a venturi creates an area of low pressure. This low pressure literally sucks the fuel out of this jet and puts it into the intake manifold. There is also a throttle valve shown at the top of the carburetor. This valve opens to allow more air to be pulled into the intake manifold, which in turn makes the venturi effect stronger, which sucks more fuel out of the little jet. The pilot can control the amount of airflow by adjusting the throttle control in the cockpit. The control is shown at the bottom as the black knob. The pilot can also control the amount of fuel available to be sucked into the manifold by the jet by adjusting the mixture control. This cockpit control is shown as a red knob in the cockpit and is shown above. We have an animation of the carburetor in the next slide. One limitation of a carburetor system is that it can get ice forming around the venturi, which can restrict or stop an engine. Remember that a venturi causes low pressure, and this also causes the temperature to lower at the venturi. If the temperature goes to freezing and there is enough water present in the air, ice can develop in the venturi. Inside the airplane, you would know you were getting carburetor ice if the engine started running rough and there was a drop in power, or RPM, shown on the tachometer. Fortunately, most modern aircraft have a carburetor heat system. The carburetor heat is hot air from the exhaust manifold that is redirected to the carburetor by means of a cockpit control called carburetor heat. When this is switched on, hot air from the exhaust is delivered to the carburetor, which melts the ice. The pilot will know that it's working because the engine may get a little rougher due to the ice melting, but the RPM should improve to near normal. When the pilot turns off the carburetor heat, the full RPM or power should be available once again. Notice on this animation that the fuel begins to be drawn from the fuel reservoir. This causes the float to start going down. This causes more fuel to be added. The float regulates how much fuel stays in the reservoir. When the mixture control is open to allow fuel into the little jet, air begins moving, causing the venturi to suck out fuel. It then gets delivered to the throttle valve, which is connected to the intake manifold. As the throttle valve opens more and more, it makes the venturi create more and more low pressure. This drops the temperature at the venturi and ice begins to form. The switch at the top left simulates opening the valve to allow hot air from the exhaust manifold to heat up the carburetor and melt the ice. If you need to see the engine in action again to see how the carburetor plays the role it does, go back in this presentation to the 4-stroke animation. So the last thing we need to explore to finish off how the engine works is where the spark comes from. In order to ignite the fuel-to-air mixture in the cylinders, which was provided to us by the carburetor through the intake manifold, we've got to have a source of ignition. The ignition comes from a device called a magneto. You don't need a battery, alternator, or any other electricity to make a magneto work. Magnetos are found on, believe it or not, lawnmowers. If you have an engine-driven lawnmower, then you probably have pulled that cord to start your mower. You didn't have a battery or anything else, just the cord. The pulling of the cord caused the magneto to turn inside, which generated electricity. So basically, one of the useful things a magnet can do is generate electricity. It does it by creating a magnetic field which is then passed over a coil of wires. Why a coil? Well, if it were just a single wire, we wouldn't generate very much electricity. The more coils we make, the more electricity we make. We can also spin the magnet faster to generate more electricity, but it's just easier to make a bigger coil. The image here is a magneto. This attaches to the back side of the engine and uses the crankshaft through gearing to spin it. So here is the opened area of a magneto. See the gear on the top? See the coil on the bottom? The coil is protected in the black case. Also notice the little switch in the upper right. There are usually two magnetos on an aircraft to provide better ignition, and in case one fails, the other can still provide ignition. The magnetos are selected either both at the same time, which is the normal mode, or the left and right one can be selected independently. The pilot decides this by use of the key switch in the cockpit. If both are selected, then both magnetos are supplying electricity to the spark plugs. This is the most efficient operation. If the pilot selects either L for left or R for right, then one magneto is switched off, and only one is providing electricity to the spark plugs. This causes a drop in engine RPM, which is shown on the tachometer. If the pilot selects off, then both magnetos are not providing electricity to the spark plugs, and the engine will stop. It's important to know that even when the key switch is turned to left, right, both, or off, the magnets are still spinning. It's just the electricity is not allowed to flow to the spark plugs. So here is an animation of one of the two magnetos. Notice how the magnet is spinning along with the contact breaker and distributor. These are all timed together. The distributor connects to the spark plugs for each of our 4 cylinders, which are represented by number in the bottom right of the animation. The spinning of the magnet across the coils causes a spark. But wait a minute, where's the spark? The magnet is spinning from the crankshaft and everything is turning or timed correctly, but there is something wrong. Look over at the switch on the left of the animation. It's closed. This is basically taking the coil and destroying the electric field. It's what would happen if you turn the key switch on our last slide to the off position. It will open up, and you'll see the magnet's influence across the coil, which causes electricity to be generated. There is another coil next to it, which basically steps up, or increases, the strength of the first coil. This is applied to the distributor, which decides which spark plug to fire next. This is the end of this lesson.